My name is Saborno Isaac Berry, and I'm the youngest student ever at NYU, doing my major in math and my minor in physics. And today, we're doing modern algebra, part 3. So, let's get started. Last time, we talked about permutations, right? Essentially, what happens if we take a set like x is equal to 1, 3, 5, 7, 9. What if we take this set and then we just rearrange all the elements in some arbitrary order? Like, for example, 5, 7, 1, 9, 3. Then what we can do is we can create a function from x to x. This is what we call a permutation. So this function in particular would map 1 to 5, 3 to 7, 5 to 1, 7 to 9, and 9 to 3. So today is going to be a little bit short, but essentially what we're going to be doing is we're going to be introducing the notion of a group.
I thought we covered group last time.
Yes, but not completely. So, what is a group? Well, a group is just a set of elements such that they are given an operation, like for example addition or multiplication, or any binary operation, or where you can compose two of the elements, and they have to be associative over composition. There has to be an identity such that any element times the identity is equal to the identity times that element, which is equal to the element itself. And there always has to be an inverse. So that inverse, for example, could be, if we take AB, this is equal to BA, which is equal to 1. So the first thing we're going to do is we're going to prove there's one unique identity for any group. And to do that, it's crucial to have this inverse in mind. So, essentially, let's say there is no unique identity. We've got two identities then. A left identity such that LA equals 1. LA equals A. Well, and a right identity where AR is equal to A. You see what I mean here? And of course, you can see here that the requirements for being a group under a certain operation do not necessarily include being commutative. Of course, if you're commutative over that operation as well, that would make you an abelian group. But that's not what we're looking at right now. We're just looking at the general case, which allows us to know that LA and AL aren't necessarily the same, and AR and RA similarly aren't necessarily the same. So now, let's try to prove that L is equal to R, so we can prove there's one unique identity. So then, what would have to happen is, since we know there's an inverse for everything are our two non-unique identities, well then, we can just compose the two. And this can be equal to E, of course, or this can be equal to F. Or let's say we have maybe a left identity such that LA equals A, and a right identity such that AR equals A. Then what is LR? Well, LR can be equal to R, or LR can be equal to L. So that means that L must be equal to R. So in any general case, that means that the two identities have to be equal. And of course, this can hold for more than 2 as well, although I don't see why you would have to prove this. So, there it is. That's how we know that we can have a unique identity. All right. So now, let's get to non-abelian groups. Now, abelian groups are the ones that we can think of off the top of our head. Like, for example, we can have the integers over addition. Or we can have the real numbers over multiplication. Some might interpret this as being only the positive integers, so it's usually better to opt for writing groups like this. Man, the lag on this is horrendous. So, now that means we have 2 abelian groups right here. What makes them abelian? Well, oh shoot, the real numbers are should be addition. Okay, well, what makes these abelian, wait, crap, it is, sorry. So what makes these abelian groups? Well, first of all, is addition associative? Of course it is. We all learned that in 2nd grade. Is there an identity? Yes, there is. For addition, that's the 0 element. For multiplication, that's the 1 element. Both of them are in their respective sets. And finally, we've got the inverse. Is there an inverse? Of course there is. Here, in the integers, it's going to be the negative numbers. For example, we have 5 plus 6 is equal to 11. Then the inverse there would be negative 6. So, essentially, what I'm trying to say is that A composed with its negative variant is always going to be equal to the identity. And, oh, it looked like I made a little slip up earlier. This should be E for the identity. All right, great. So, what about the real numbers? Well, over multiplication, the inverse is obviously division. For example, we can divide 1 over 3. So, we compose 3 and 1 over 3 via multiplication, and we get the identity, 1. All right, so those are some abelian groups. Now, let's get into non-abelian groups. Now, the simplest one you can think of off of your head, probably the integers over multiplication. Why? Well, it's associative. Yes, it is. It has an identity in the integers. Yes, it does. That's 1, which is an integer. But it doesn't exactly have an inverse, you see. Because if we take 2, what integer do I multiply by 2 to get 1? The multiplicative identity.
Yes, 1 over 2.
It has to be an integer, unfortunately, which means that there is no inverse within the integers. All right, so now let's talk about finite non-abelian groups, which are usually a lot more interesting. And this time, we're going to be calling back to permutations from yesterday. Specifically, what we're going to be doing is taking the symmetric group S3. So what is this group? Well, it's essentially recording all the permutations of the set 1, 2, 3. Pretty simple, right? Well, I can write down 6 permutations I can think of. The identity function, backwards, I guess, transposing 1 and 3, transposing 1 and 2, transposing 2 and 3. What else? Let's see. This is only 4 when I know they're supposed to be 6. So then we can apply the transpose twice to get 3, 1, 2. And we can also apply the transpose here to get 2, 3, 1, which makes our 6 different permutations. 1, 2, 3, 3, 2, 1, 2, 1, 3, 1, 3, 2, 3, 1, 2, and 2, 3, 1. So now we can actually express these different permutations as combinations of only 2 permutations. Using cyclic notation from yesterday, if you don't know what that is, go watch the previous. We can record this right over here as permutation alpha, and this right over here is permutation beta. Now, you may ask, why just this? Where's the 3? Well, the 3 maps to itself, so customarily we don't include it. All right, so in a more familiar way of writing it, we write 1 goes to 2, 2 goes to 3, and 3 goes back to 1. And here we can write 1 goes to 2, 2 goes to 1, and 3 maps back to 3. So you can see these are actually 2 of the unique permutations that we just had earlier. So it doesn't take a genius to see that if you apply alpha 3 times to itself, since it's just cycling the integers 1 over, that means that this multiplied 3 times by itself, this operation composed 3 times, this permutation composed 3 times is going to be the identity. And of course, in the same way, this composed twice is just going to be the identity. Since we swap 1 and 2, we swap them back, then it just gives us 1, 2, 3 again. So that's pretty simple to look at. But what are the other relationships? All right. So the last property we can verify is that beta alpha is equal to alpha squared beta. Of course, this in terms of composition. And of course, this isn't hard to verify either. What happens when we first compose alpha with beta? So we first do alpha on the set, going from 1, 2, 3 to 2, 1, 3. And then we perform beta on the set, which causes everything to cycle to 3, 2, 1. And so that's what we get on this side. And this is, of course, equal to alpha squared beta is equal to beta squared alpha. So, of course, that's not hard to see. First, let's try alpha of beta. So first we turn from 1, 2, 3 to 2, 3, 1 via beta. And, 2, 1, 3, sorry. And then we permute those to get 3, 2, 1 via alpha. And then for beta squared alpha, all we're doing is we're transposing twice. So first, we're taking 2, 3, 1, and then we're transposing twice. Beta alpha is equal to alpha squared of beta. So first of all, we take alpha, which changes it from 1, 2, 3 into 2, 3, 1. And then by beta, we just permute 2 and 1 to get 1, 3, 2. And of course, alpha squared beta, first we apply beta, which just permutes this to 2, 1, 3. And then we apply alpha twice, which cycles everything up to first get 3, 2, 1. And then you cycle it again in order to get 1, 3, 2. So that's easily verifiable. All right, so now to actually talk about how we can obtain everything else from these 3, we're going to be using what we call the cancellation law. And yes, it's exactly what you expect. It has very much something to do with actually canceling things out in an equation. So, assuming that composition is defined multiplicatively, which basically means our operation is kind of like multiplication, like for example the dot product or matrix multiplication or something in that vein. If our composition is defined in that way, and we have entities A, B, C, then if BA is equal to CA, or if AB is equal to AC, then that means that we can infer that B is equal to C, right? And one more thing, if AB is equal to A, or BA is equal to A, then B is the identity. All right, great. So then, using that, what can we deduce? Well, the unique things we can obtain are, of course, this is going to be the identity. And what are the other ones we can obtain? Well, we have the identity, alpha, beta. Alpha squared is a no-go because that's just the identity. Alpha cubed is a no-go because that's just the identity. Beta squared is also a no-go because that's just the identity. So we can apply alpha, beta. We can apply beta, alpha. And so far, that's 1, 2, 3, 4, 5 combinations. And as you can probably guess, the sixth combination is not going to be alpha squared beta, since that's the same as beta alpha. It's going to be beta squared alpha. So what actual permutations do these correspond to? Well, this one, as you can guess, is 1, 2, 3 for the identity. Alpha, as you can guess, once again, is just cycling them over to get 2, 3, 1. Beta is just permutating 1 and 2 to get 2 and 1. Applying alpha after beta is going to give you, applying alpha after beta is first going to transmute these two to 2, 1, 3, and then we get 3, 2, 1. Applying beta after alpha is going to be the same as alpha squared beta and give you 1, 3, 2. We know that alpha squared beta is a no-go because it's just beta alpha. We also know that beta squared alpha is a no-go because this is just the identity, so that would give us alpha again. So the only way to go would be beta squared is a no-go because that's also the identity. So all we have is alpha squared. So what happens if we apply alpha squared? Well, we go from 2, 3, 1 to 3, 1, 2. Which is the final permutation of all of these. So writing these down, this 2, 3, 1 is alpha. This is beta. This is alpha beta. This is beta alpha. And this is alpha squared. All right, great. This is the last symmetric group we will actually be covering because symmetrical group 2 is really easy. And as n increases, it gets increasingly more complex because, of course, the number of elements in the group will increase the same as n factorial because that's how many permutations there are of the integers up to n. We've got 2 permutations, 6 permutations, which is the amount of elements we had right over here, up to 24 permutations. It'd probably take like 2 videos just to do S4, and then, of course, 120 permutations and so on. This could probably only be done by a computer, and so on and so forth. So, of course, this gets really, really hard as you go on, which is why S3 is the sweet spot. So, that's all about groups, abelian and non-abelian groups. Here's the final image. Thank you, everybody, for watching.